Hi everyone, we are Innova Data Hub team and we are representing Innova TCN on the SAS Hackathon.
Innova is passion for technology and constant challenges. Innova works every day in order to offer our customers solutions as unique as their businesses. Every Innova project is a new adventure where commitment and excellence go hand in hand in order to offer solutions which are real and on the cutting edge. Using machine learning algorithms to forecast the customer's behavior, artificial intelligence solutions for creating developed real-time classification systems, text analytics for finding patterns in social networks, and much more. This is backed by our expertise and our experiences, tested in our analytics and big data laboratories, and successfully tested in international competitions. Innova TSN offers an end-to-end service, from the detection of the need, the design of the solution and its implementation, to its maintenance. There's a long way to go, and at Innova TSN, we are ready.
Big cities, such as Madrid, have a huge problem with pollution and urban mobility. Although those cities usually have sustainable transport alternatives, some of them have an underperforming service and discourage people to use them. By using both technology and advanced analytics techniques, the service can be improved and optimized, and eventually it may help to change citizen habits regarding urban mobility. In order to have more humanized and sustainable cities, there are a few different alternatives to use, such as walking, ride scooters, use public transport or ride a bike. In Madrid, we have a public transport service which is called Bicimat and is provided exclusively with electric bicycles. Consequently, the aim of this challenge is to optimize Bicimat service using advanced analytics to study and predict the demand and to create forecast models to provide the number of bicycles demanded for each day and different time slots. In order to develop this case, we use three datasets. One of them is the bicycle data usage, another one is the information of the docking stations, and the third one is other variables, which includes weather information and special events. I hope you enjoy this video. Have fun.
To approach this exercise, Innova gathered a bunch of data provided by Madrid City Council, which is publicly available. This data allowed us to predict the demand of bicycles and identify possible improvements to the service. First, the dataset is prepared. Second, a demand forecast is worked out on an hourly and daily basis, applying different algorithms. And lastly, the optimization phase will provide a better understanding and management of anchor availability and bicycle replacements. For the implementation of the exercise, Innova used some Python libraries which are available at SAS Via from the Jupyter Notebook environment. We've used in SAS Enterprise Guide for the ETL process and SAS Forecast for the Sarima modeling, and as we find it very useful when dealing with plenty of time series.
The data available about Bicimat service that has been used is data related to the trip, such as departure and destination, duration of the trip, location and capacity of each station, and finally the number of bicycles available and docked. To complete this data, the weather information from the closest weather station to the Bicimat station has been added. Also, the Madrid holiday calendar has been considered. Some important information we gather is 200 active stations in the analyzed period from 266 stations in the dataset. The bike capacity range per station is between 12 and 30 bicycles. Lastly, 89% of parking bases in active stations present activity during the day.
We wanted also to analyze the closeness of Bicimat stations to other transport stations or office areas. According to this, we have concluded that almost half of the Bicimat stations are within 1 kilometer radio from an office area and almost 60% within 1 kilometer radio from a transport station. Additionally, we have considered transport activity strike days during the analysis period, resulting in 30 days in this period. And finally, we shouldn't forget the lockdown that happened in this period due to the COVID.
This graph shows the daily average Bicimat uses per month. We can see a huge drop in April 20 due to COVID lockdown and also a big drop in January 21 due to a meteorological incident in Madrid called Filomena. The most demanded stations are close to the center of Madrid, the most touristic zone.
An accurate prediction of the plugs and unplugs in every station each hour of the day is crucial for the optimization. Analyzing the historical data and identifying trend and seasonal patterns is the base of the forecast, but we shouldn't forget other external factors that may impact these values. Data related to the weather, such as temperature, rain, or wind, but also other unexpected facts, such as technical issues in the stations, public transport strikes, etc., may affect the demand of bicycles and should be considered in the models. We have enough historical data to identify the patterns. We count with information on plugs and unplugs for each station at each hour of the day from August 18 to June 21. A strong seasonal component and growing trend since early 2020 can be observed. However, some situations, as the city lockdown, Filomena snowstorm, and even some technical issues for the whole Vitimat service are altering the demand. Also, rainfall, temperature, or wind may have an impact in the proportion of trips made by bicycle. It's important to understand the difference in the hourly patterns of plugs and unplugs depending on the day or the season. For example, the peaks of unplugs in the rush hours of weekdays don't exist in the weekends, when there is more activity at midday. Moreover, there are also different patterns depending on the month. The demanded units and hourly distribution follow a different pattern in May than in August. There are also differences depending on the stations. Stations located close to the office areas have peaks of plugs in the morning, while unplugs are more often in the afternoon. We have decided to use 4 different models to forecast the plugs and unplugs with a time horizon of 1 week. 3 validation sets have been established, each of them in different year periods and different week of the month. The second validation, for example, falls on Easter. The best model is the one whose mean absolute error across the 3 periods is the smallest. Sarima models are traditionally used in time series. They are used when there is a strong dependence on historical, seasonal, and trend patterns. In order to compare different strategies, we built 2 models with different time intervals for each station, hourly and daily. Both models give similar results, but the first one spent much time and resources, so we have selected the second one. In order to obtain the results by hour, we disaggregate the daily forecast according to the historical behavior and considering also the day of the week, as we have observed different patterns depending on if it was Sunday or Monday, for example. Main reasons that led us to use XGBoost are the speed of execution, the usual good performance of these algorithms, but also the ease of introducing external variables. Regarding the data preparation, apart from the calculation of all the lagged variables, we encoded the temporal variables such as hour, day of the week, and the month as cyclical, using the sinus and cosinus functions. We also drop records with plugs or unplugs equal to 0 due to exceptional events that we have mentioned, such as COVID, technical issues, etc. We realized that doing this, the performance was better. This is one of the advantages of using a machine learning algorithm for forecasting. With regard to the modeling process, Bayesian optimization has been used for the hyperparameter selection. Like GBM, carries out leaf-wise growth instead of level-wise growth done by XGBoost, being faster in the training. Moreover, it's possible to introduce categorical variables. The data preparation and modeling process is very similar to the XGBoost model, creating lagged variables, removing outliers and missing values, and using automatical hyperparameter tuning. LSTM are recurrent neural networks that learn from sequences, capable of modeling short and long-term dependencies thanks to the persistence in memory of information from previous states. They stand out for their ability to deal with the vanishing gradient problem. But one of the limitations that we found using this algorithm is the lack of memory when dealing with long hourly series.
With the goal of improving Vitimat management system, it is necessary to optimize the process of picking and supplying bicycles. This optimization will minimize the number of impossibilities, meaning the number of bikes and dogs that exceeded the capacity at the time of demand, and also will reduce costs associated with transport. The result of the optimization will be the number of bicycles to be replaced or dogs released at each station at each hour of the day. In order to do this, we should know the known demand who has been satisfied in the past, and the lost demand, which is users who has not been satisfied because there were no bikes or dogs in the stations. Therefore, to estimate known demand, we take advantage of the forecasting models we described before, while the lost demand must be simulated considering different scenarios. We consider different algorithms that can solve the problem. We consider hill climbing algorithm and heuristic algorithm that obtain the best solution in a reasonable time following the direction of the objective function. We also consider simulated annealing and stochastic global search, which imitates the phenomenon of solid annealing. It is like hill climbing algorithm, but in each iteration modifies the solutions and searches in a neighboring area of space until the local optima is located. It also accepts worse solutions according to temperature. Besides, we consider genetic algorithm, a such heuristic inspired by Charles Darwin's theory of natural evolution. It works with sets of feasible solutions which intersect with each other and mutate to construct new solutions. These solutions compete with the first to survive. Finally, we opt to use simulated annealing. We chose because it escapes from local optimums, it speeds up the convergence process, it incorporates a sophisticated neighbor search process that guides the evolution of the process, and also because we have previous experience in other complex processes. This optimization must be produced for all active stations in the city of Madrid in a computation time limited to 5 to 10 minutes. In our problem, we have multiple objectives. As we said, the main objective is to minimize the number of impossibility, number of people who cannot use the Bicimat service. The secondary objective is to minimize the number of stations with any replenishment during the day, in order to concentrate the supplying at certain times and reduce transport costs. As we said, the input data for the optimizations are capacity of the stations, status of the stations at hour 0 of the day, demand forecasted as known demand, and random scenarios as lost demand. We require that bicycles replaced or withdrawn may not exceed the capacity of the stations and the availability at the time. We have a limited number of bicycles in stock, and no more than a maximum number of replenishment may be made per day and hour. As explained before, the algorithm is based on the idea of generating neighbor solutions. A neighbor solution is proposed from a given solution, very similar to the original one, to further improve the objective function. Aiming to elaborate the neighbor solution, a change is made at a random hour and station so that constraints are satisfied. In this new neighbor solution, two different changes can be made: remove the repositions or modify the repositions in a pseudo-random way, analyzing the future demands at that station.
After applying different forecasting techniques for the prediction of plugs and unplugs for the following week for every station, we analyzed the mean absolute error of each station provided by the 4 models tested, and we realized that there wasn't a unique winning model. So we ended up selecting for each station the model with the lowest error. Here we have some examples showing this. Even though XE-Boost shows a very good performance in general, it doesn't across all the stations. For example, the prediction for Puesta del Sol B is better with Arima, while for the station Plaza de Ramales is better with Light GBM. And for station Alcalá, the winner model has been LSTM. Seasonal patterns or the influence of external variables could make that the fit with Arima is better for some stations, while for others is other type of machine learning model, or even a neural network. XE-Boost was the winner model in 88% of the stations. The most important features are the lagged, plugs and unplugs, the day of the week, and the meteorological variables such as the rainfall or the temperature. The day of the week and the bank holiday flag are also among the most important features.
In order to test the optimization implement, executions have been carried out on 4 different days, considering the predictions obtained for those days, including the lost demand. The starting point is high values of impossibility or unsatisfying customers, above 1,000 in all cases, which the algorithm will deal with respecting some restrictions. These restrictions have been obtained by studying the repositions carried out by Bicimat between 2018 and 2021. This gives a maximum of 240 repositions per day. The algorithm used is simulated annealing. It has the ability to worsen the objective functions in order to escape from local optima. This characteristic can be seen in the evolution of the algorithm. In the first graph, one can observe these rises in the objective function where worse solutions are being accepted. And as the temperature parameter decreases, these rises in the objective functions are also reduced. The second graph shows the best solution obtained so far. The execution time is usually around 5 minutes, stopping the process if it reaches 10 minutes. The results obtained on a daily level are very good, reducing the initial impossibilities by around 87% without reaching the maximum limit of repositions. It reduced the number of impossibilities by more than 1,000 units. This will translate into more than 1,000 more satisfied customers per day for VisiMath services. Here are the results at the hourly level on one day. The optimizations start to assign repositions during the day. The first hours of the day are more difficult to solve as fewer changes can be made before them. The first two graphs show how the repositions placed begin to have a great effort from hour 4 onwards, where more than 80% of the impossibilities are solved. The last graph shows the repositions placed versus the maximum repositions, always respecting the restriction. Finally, we analyze the impact of the solution reached at the stations with the highest demand. Note how in most of them the number of impossibilities is reduced to 0. The second graph shows the percentage of impossibilities satisfied, with an average of 91%, as well as the repositions that have taken place in each station.
Variables related to the weather are assigned on a daily basis and in a central point of the city. The availability of these variables split by hour in each city zone could improve the performance of the model. Hourly disaggregation to split the daily forecast have been made in a naive way, just considering the average distribution of a concrete period per each station and day of the week. It would be possible to apply other techniques such as generalized linear models to make this split and obtain more accurate results. Using exponential smoothing and inputting null values in the past due to exceptional events such as COVID lockdown or VisiMath issues could be another way to improve the results. Use of walk-forward validation to update the model with the values of the previous day to get more accurate results. The spoiled solution provides a resource to the VisiMath management system that informs of the replacements to be made at each station throughout the day. This improves the service provided with a specific objective to avoid situations in which the user cannot make a trip due to the unavailability of vehicles or dogs. The integration of the solution with the VisiMath management system requires that, in addition to provide the number of supplies per station, report the van route to make these supplies. This route should be based on the available resources and the standard resources as number of vans for transporting bicycles, number of workers per hour of the day, among others. Finally, we get to the conclusions. They are classified as demand and forecast conclusions and optimization results. Firstly, and regarding the result of demand and forecast models, we can conclude that the exploratory analysis has provided crucial results that has helped the team to approach the modelization strategy. The most important feature for the machine learning models are the lagged variables and the day of the week. Nevertheless, some external variables improve the performance of the model. Those variables related with the weather, especially precipitation and temperature, are the most relevant. Having them split by hour could improve the results. Furthermore, the optimization has shown some results that are worth highlighting. Firstly, the execution times of the optimization model is between 5 and 6 minutes. It allows us to obtain a quick solution that can be integrated rapidly in VisiMath systems. If VisiMath is to follow the recommendations of the model, impossibilities will be reduced by an average of almost 87%, which translates to more than 1,300 satisfied customers. Given the difficulty to make replacements during the night, the majority of the impossibilities occur during the first hours of the day. Finally, in the 20 dock stations with more demand, impossibilities are reduced more than 90%. We would like to thank SAS for the opportunity to participate in this hackathon, and we hope there will be many more.
Furthermore, we want to recognize the incredible job that all the Innova team has performed. All of them are an essential component of the success of this initiative.
We also would like to acknowledge not only the award winner teams, but also the teams that have participated in the competition.
Thank you and goodbye.